Hello, we are Team 25. Our team includes Mara, Gabby, Danielle, Andrew, Alex, and Michael. And today we are presenting our final analysis and redesign of a toaster. So here's just a quick product description. So a toaster is a user-friendly and simple kitchen appliance that you can use to lightly cook and toast bread slices. Here's an exploded view and an assembled position of our product. So our primary customers are going to be those in the service industry, and the anticipated volume here is 600,000 units per year. Whereas our secondary customer is going to be a typical household family, and the anticipated volume of units per year is 17,000. Here is our FAST diagram. And then with our FAST diagram, we were able to create a function component mapping matrix, which we were able to later use in our redesign. And then we created a bill of materials for our product. And with this bill of materials, we were able to create a quad chart, which shows manufacturing costs on one end and the functional importance on the other.
Next, we created a functional differentiation table, which was used to split up the functional requirements that were the same for both customer groups and different for each customer group. And using that, we created the component commonality table, which split up the components into components that are the same for both customer groups and different for each customer group. Using those two, we were able to create the final toaster assemblies. The one on the left is for the primary customer group, and the one on the right is for the secondary customer group. The main difference is the back covers. The one on the left is for the primary customer group, and the one on the right is for the secondary customer group, which has a safety that's made from insulating material. And this just shows the interface between the back cover and the outer shell.
To realize delayed product differentiation, we pushed the addition of the back cover to the end of our assembly sequence. We were able to calculate a total manual assembly time of 144 seconds, with 19 theoretical parts that gave us an assembly efficiency of 39%. For our redesign of our platform part, we chose the internal plates because they were high in importance and high cost portion of the quad chart. We only had one module part, which allowed us to easily select the back cover for redesign. For redesigning the heated plates, we combined two plates by adding a connector along the bottom edge. Each plate has a slight curve to it now at the bottom as opposed to ending at 90-degree angles. The DFA guidelines that led this change were reducing part count, as now we have 2 parts instead of 4. Also, by connecting the plates, the heated coils are always facing inward. Finally, we follow DFA 10, which is helpful because there's no need to keep holding the plates after insertion. For the back cover, we decided to make it a snap fit instead of a screw. This reduced fasteners and reduced part variety, and now the top cover, we can get rid of the little tab that's circled, and you can see where the snap fit is fitting on the right picture. Through our redesign, it's shown we made good choices because our assembly time decreased and our assembly efficiency went from 39 to 49%. Highlighted in green are the changes that our redesign caused. It was especially helpful that we reduced the part count by getting rid of screwing on the back cover and reducing the number of internal plates. We predict the cost change of adding the snap fit to be rather minuscule. There will be a change in the price for the internal heated plates because of the additional material, but we don't think it'll be detrimental.
We decided to use automated assembly for the control assembly and also to redesign the control assembly. We had 3 design goals in mind. For DFA 1 and 13, reducing part count and avoiding adjustments, we wanted to combine the actuator holder and the ejection bars and make them one part. To remove a step from the support was our second goal. It helps us with DFA 6 to increase part symmetry. And also, we removed the hook-like corners on the top section of the support, and this helped us avoid tangling and nesting, which is DFA 8. In this table here, you can see design for automated assembly before our changes. The total assembly cost pre-redesign was 27 cents. The redesign is shown here. The before pictures are on the left and the after pictures are on the right. In the top left, you can see we removed a lip from the support to avoid tangling and nesting of the support part. In the top right on the left, you can see the actuator assembly. It was 3 parts, but on the right, we made it 1 part. On the top right, you can see that we combined these 3 into 1 part and also added material to add symmetry to that part. And on the bottom, on the left, you can see there was a corner cut out in the support, and on the right you can see that we filled that in. As you can see in this table, after redesign, our cost is 4 cents, which is a total decrease of 22.6 cents.
Here's a dimension model of the internal heated plate design after DFA. The critical dimensions were based on FCMM requirements, and this is shown on the right side of the slide.
Here's the isometric view of the model with dimensions added. And we can see that the dimensions correspond with the FCMM requirements on the right.
For selecting manufacturing processes, we used info on the part, such as its material, shape, mass, thickness, tolerance, surface roughness, and economic batch size. For the internal heated plate, our shortlist was sheet metal forming and machining. We decided to go with sheet metal forming because the part has a relatively simple bend. For the actuator ejector bar combination, the shortlist was die casting and machining. Die casting was chosen because of the part complexities.
For the cost estimation of the internal plates, some important notes are that the material was aluminum, there is not scrap metal, and we assumed that the part would be cut off. And we also assumed that it would be produced in 2 steps. Step 1 would be shearing the part, and the second step would be bending it into its final shape. The final total cost of the internal plates would be 88 cents per part. For the cost estimation of the actuator holder and the ejection bars, we assumed 1 side pole required and a single cavity die. A main contributor to cost is that the parting surface type, which is a complex curved surface with steps. The final cost of the die casting part would be 57 cents per part.
Here's an isometric view of the DfM redesigned actuator and additional 2D views to help you better understand the dimensions. For the redesign, we added draft angles to the actuator in order to make removal from the die easier. Also decrease the rib thickness to 80% of the wall thickness as specified in the DfM, and rounded the edges to provide more strength and not have weak corners. Additionally, we increased the wall thickness to 1.1 millimeters, which is within the range for die casting.
Here's what the internal heated plates look like after DfM. All the critical dimensions were kept within the specified tolerances. Here are the 3 things we changed with DfM. The first thing, we changed this kind of this flange part at the top that would need a V die and with a tight angle into a wider angle. The second thing we did was DfM Pro suggested. Basically, we changed all of the bends to 12 millimeters instead of 2, which is 6 times the material thickness. The third thing we did was remove the ridges that were basically there for surface area and heat radiation. We thought that removing that would help us a lot with the manufacturing costs without losing a lot in the performance. Here are the quotes we received from hubs. We interpolated the data and found that the price estimations for hubs were closely in agreement with our analytical estimations. Here we can see the post redesign costs for both parts after DfM. We can see that the sheet metal part went down by 2 cents and the die casting went down by 14 cents.
For our product as a system service, we thought of adding electrical components that connects the toaster to an app that users can download on their phone. This could allow for the toaster to only be on during automatic scheduling, reducing the electricity consumption. This, coupled with the potential of making the toaster rechargeable, would get rid of phantom energy usage. Additionally, this app could have different user profiles and track how much power the toaster is using. This PSS would result in a higher cost for research and development, as well as the additional components.
So to conclude, we were able to reduce the part and the complication of those parts to help in manufacturing and assembly, which would decrease the cost as well as maintaining the function of the product. Unfortunately, this would not make manual assembly more efficient, and there would be a lot of excess material. Another approach we could have taken was to find a CAD model that was in English and to focus on the plastic components. Thank you very much. And does anyone have any questions?